Good morning or good afternoon, depending on where you are in the world. And welcome to today's webcast, Cost-Effective Long-Term Fluid Inflow Measurement Without Wires or Well Intervention. I'm Pramod Kulkarni, Editor-in-Chief of World Oil Magazine, and I'll be your moderator today. During today's presentation, you'll learn how chemical tracer technology can help you optimize development plans to increase reservoir production and reduce costs. Adding chemical tracer technology to your reservoir surveillance toolkit can enable you to gather vital oil and water inflow data from your lower completion with no costly intervention, saving time and money by building up a long-term and continuous picture of your well's production performance. We would like to thank Tracerco for putting together today's exciting event. Joining me for the event is Stuart A. Brown, Tracerco Global Business Development Manager for Reservoir Technologies. Stuart is approaching 25 years of experience in the oil and gas market, working within drilling, production, and reservoir departments, both in engineering and in management roles. Having started his career with Halliburton, he has held several roles over the period, gaining expertise in engineering, well construction, cementing, and stimulation through to well intervention and modular drilling. His role as Business Development Manager for Tracerco's Reservoir Technologies business sees him lead the commercial function. He and his team work with customers to design reservoir surveillance projects that use advanced chemical tracer technologies. Stuart has worked at Tracerco for 3 years. In that time, he has worked with over 100 customers across more than 40 countries on reservoir management strategies, allowing them to optimize development plans, meeting or even exceeding the objectives for their oil and gas fields. Following the talk, we'll have a short question and answer session. You can participate in the Q&A session by asking questions at any time during the presentation. Just type your question into the Ask a Question text area in the bottom corner of your screen and then click the Submit button. You may enlarge the slide window at any time by clicking on the Enlarge Slide button, which is located below the presentation window. The slides will advance automatically throughout the event. If you're experiencing problems with the program, please press the F5 key on your keyboard or close your window and relaunch the presentation using another media player. You can also visit our webcast help guide by clicking on the Help button below the slide window. Now let's get started. Stuart?
Thank you for the introduction, Pramod, and thanks to everyone for taking the time out to listen to this. Okay, let's run through this, the Drill Smart, Yield More, Hydrocarbon and Water Inflow Tracer presentation. Today we'll run through some of the tracer insight, some of that science that goes on behind the tracers, the deployment in the field, the polymers and how they're engineered, data and analysis, the theory behind, and then we'll look at some case studies, 3 of them, and as Pramod said, we'll take some questions towards the end. So let's look at why we'll be using tracers. What is the need for running tracers? Well, you can imagine, especially in multilateral conditions where you have multiple wells running back to a common mother bore, we have a situation where we might want to find out what oil is being produced, where is the oil being produced, and what quantities, which areas are producing water, and at which location is that water coming from, even to the point where could we drill next for the future wells. So the science behind tracer is only released on a number of factors here, and it's shown as fluid properties being important, whether they're heavy oil or light oil. Temperature has an effect, so the higher the temperature, the more tracer is being released from the polymer. we also have the surface area contact, which is extremely important, as this depicts how much of that tracer in the polymer is exposed to the targeted fluid. And we measure the amount of elution, as we call it, or tracer release of molecules, in milligrams per centimetre squared per day. So this tracer is detected at surface in samples, but only when that tracer is being released from the polymer, which only happens when that particular fluid is coming into contact. So an oil will only affect an oil tracer, and water will only affect a water tracer. So these tracers are completely dormant when they're not in contact with the fluid phase. And it is not directly related to flow, which may be a common misconception that is believed to be that the higher concentration being released is necessarily more. We'll discuss that in the future slides. So at the moment we're working on building up our tracer library. We have 33 field tried and tested oil phase tracers right now, pushing that to over 40 currently now with our research and development, and over 40 unique water tracers that can be used in conjunction with each other and are completely independent of each other as well in the same fields and reservoirs. The field deployment. How do we run them? Well, clearly this is an inflow process, so we need to look at how do we get the tracers to the location of interest. Now, as they remain passive, we can put them down on the completion, and they can remain there dormant until that target fluid is being produced, or if the well is being shut in for a period of time during future completion plans. And these run in with the screens or at some part of the lower completion, and we install these along with the brand newly completed well so that they're in preparation for being produced back when that well is ready to do so. These then go down into the zone of interest and they remain fixed and will stay there for the life of the well. The polymers do not deteriorate or change in any fashion. The tracer, of course, has a lifetime. However, the polymer is solid and will not move from position. So let's have a look closer in at this. We have the wellbore close-up here of this particular screen, and we see that as the fluids are coming into the screen across the mesh or the wire wrap, it will then come across the tracers that are installed behind here, make contact with the polymer where the tracers are, and as they do so, they will pick up the molecules of tracer that are in the interstices of the polymer throughout the entire surface area of that particular polymer, make contact, pick up the tracer, enter the wellbore, and now, as you'll see, the oil in this case is tagged with the chemical tracer, which then travels back to surface. We're talking parts per billion to parts per trillion in levels of detection here, which is, as you understand, very, very minute quantities that are detectable by our laboratory equipment when we analyze them. So at this point, you can see the tagged fluid has now been released. It has seen the targeted fluid pass over it, and because of this long, controlled, sustained manner that these tracers release in a constant elution profile, we can calculate the inflow. We can work on the qualitative where that tracer is coming from because it's unique, and this can last up to potentially a number of years. Okay, just a quick question we'd like to ask you at this point. What we're going to do is ask you a poll question. When do you see the price of oil rising again? It's just a multiple choice. It doesn't have any bearing on the presentation. It was just something that we would like to ask you as a group to come back with an answer. So if I give you 20-30 seconds to make your answer, please do so and submit it, and we'll have a look at the results once we have done that. Okay, the next slide will be the answers to that, so it'll be interesting to see what we have. That's an interesting one. So the majority of us think that we're talking over a year until the oil price rises. I think that's probably a fair estimate, but interesting to see those results. So thank you very much for putting that through. Okay, we move on. So we're in the on-site process of now retrieving those fluids back to surface. We're now sampling those fluids and we're now going to analyze them. And this is where we look for the presence of these smart tracers to determine the zonal flow inflow characteristics. And these are, as you can see, will be graphically represented, and this is what we're going to move in to discuss in the future slides. So let's have a look at the tracer polymers here. How do we choose to install these devices? Well, there's a number of options, and Tracerco likes to pride itself on the fact that we're very adaptable in how we apply these tracers, simply because not all completions are the same, not all designs are the same, therefore we need to be flexible. So we have one design here that is a completion pup joint tracer that is matched to the client's metallurgy, thread type and size, of course, so that there's no foreign or alien materials in the well compared to the planned completion. And this 20-foot joint is manufactured to include a long lifetime planned tracer elements, as you can see in pink there, that's applied to the pipe, where a mesh shroud is then applied to then protect that tracer and allow fluid inflow to come in and out of the pup joint to then pass over that tracer. And this is ideal, as I say, for long-term planned completions up to maybe 2, maybe 3 years for long-term completion information provision. In terms of completion B, where we're looking at a standard wire wrap system here, clearly the spaces as our real estate is where we can apply. Now what we like to do here is extrude our polymers to be able to fit in between these drainage layers. We clearly don't want to block up all the screens, so we're very careful as to where we apply these, how much we apply. Typically anywhere from 13 to 30% maximum of the area that we're trying to cover. These are really good for covering long sections of wells, and you can mix oil and water in here also, so that every second drainage layer can be used for an alternate oil or water system, because they can work independent of each other, and this is how the wire wrap system works. And we install these at the client's chosen location or the third-party completion company vendor's location, wherever that happened to be. And as you can see, these are pre-designed, pre-manufactured to slot straight in to the applicable screen design. Another option may be to look at our ICD port. Now, clearly some of these tracers will work in ICD conditions, but if you're looking for a relatively short-term project, you're looking to have the tracer right next to the ICD port, we can also manufacture the design to basically encapsulate around the ICD itself, with the hole not being blocked by the port, and therefore it gives a definitive answer as to which tracer is coming from which ICD. And finally, another option would be to use the premium mesh screens. Now, if we are working with the client that the screens are not yet built, we can apply our polymer to the base pipe before those shroud screens are finalized and completed. Or having said that, have the screens being made already, we can inject through a process in situ polymerization, where we inject a liquid which then hardens behind the mesh and onto the base pipe, and then gives us the same potential and the same possibilities, even though the screen's already been built. So we have that option should we end up in that situation where the decision comes late that we want to run tracers but the screens are already built. The beauty of running tracers is that in conditions where a PLT cannot be run, there may be a cost element involved, there may be a risk element, the horizontality of the well, you can't get the PLT in, and basically you don't want just to accept a snapshot in time of what the well is doing. You want to have a build-up of picture of what the well is telling you. Then clearly smart tracers come into their own. There is no intervention, there are no wires or cables to concern yourself with, therefore the risk element is reduced drastically, and there was no need to shut the well in to take the tests, as this is a product that runs with the well as it happens. So let's have a look at the theory behind this. It's often assumed in steady state conditions that the higher the flow rate, then that surely the greater the concentration of tracer. But as we can see, this is actually not the case. If I show you this example here, the flow on the left is actually slower than the flow on the right where the yellow tracer is. And because the flow is slow, it means that more tracer, because remember it's being released at a constant rate, more tracer is then allowed to become concentrated within that passing flow because it's not being swept away so quickly. Clearly, in a situation where you have a faster flow rate, you have less ability for that standard eluting tracer coming out of that polymer simply cannot fill the molecules of oil passing as quickly as it would in a slower flowing regime. And that's why in these steady state conditions that you cannot possibly say that the concentration is guaranteed to be higher if the flow is higher. And that's important to remember. It's extremely important to frequently sample. We'll talk a little bit more about that. But without it, you cannot get quantitative data. You're back to qualitative. And perhaps qualitative is all you require in a yes-no fashion. Yes, you're getting flow from that zone, or no, you're not. But as a technological company, we look to the future of bringing more data for the customer to make more informed choices and decisions. In transient flow, as the wells offloading and building up, this regular sampling is absolutely crucial. It is impossible to provide quantitative data without it. So a pulse velocity concept is that when the well is building up, we're looking at the blue tracer, which is going to be the stronger flow in this example. As it starts to flow, because it's been sitting in a static conditions with the production fluid surrounding the tracer, there is going to be a cloud, as we call it, of tracer buildup molecules. Simply a strong concentration of buildup is going to be surrounding that tracer, simply because it's been in contact for a period of time with that target fluid. Now, as there's been a lot of flow, a lot of available fluid, and a lot of contact area, clearly you're going to have a stronger pulse of data coming to surface in transient conditions. So the blue has now reached the surface, and this now starts to draw the graph. It's important to look at the peaks here. We have normalized these peaks to 1 to help balance and contrast the graphs. And you can see the peak rises and falls quite sharply, with the tail coming at the end as we reach steady state conditions further down the line. To compare the pink, which is flowing slower, you can see the shape of the curve changes. It takes longer for it to reach the surface, not only because it's further away from the surface compared with the blue, but also because it's taking longer to flow because it isn't flowing so quickly. And you can see clearly here that there's actually a higher concentration of tracer from the pink than there is from the blue. Again, back to that previous example I showed you, was clearly if you have a faster flow rate, you're going to have less tracer that's available to jump into that passing flow. And this is what's shown here. So we see these large peaks after breakthrough because the well's given a chance to static conditions to build up this cloud. We see this pulse coming to surface, which we look for. We must sample immediately on starting the well up. And again, just to clarify, we do normalize these graphs so that they're easier to compare and contrast. The important thing about steady state is that you're not going to get quantitative flow data from this point. You're going to get qualitative. You're going to find out, yes, you're getting tracer from that location, or no, you're not. So in this example, it's important to note that the blue tracer is shown at 90 barrels per day, and the pink is shown at 10. This, of course, means a surface sample is going to be telling us that there's 100 barrels coming in from those two flows per day. Now, the point here is that the background tracer response that you're seeing there just above the zero line is simply all you're going to see in this passing data. You're not going to see the peaks, you're not going to see that curve shape, you're just going to see information telling you that you've got tracer there. Now if I reverse this round the other way, so that the pink becomes the higher flow and the blue becomes a lower flow, the actual shape is going to be negligibly different. It's not going to actually change significantly, which means you're not going to be able to discern which of those zones are actually better than the other, which leads us to a problem, clearly, because it's important to know which one is faster flowing. And we can't do this in steady state conditions. So that's again another reason that it's so important to do this at the very beginning of the transient phase of the well as you're building up. Once you have this data and you know which way around that is, then that's really all you need to know. You can then reduce your sampling regime and then focus on the qualitative data. But clearly, if you want to get that quantitative, you must do this in advance. So an important point to mention here is it's clear to see that you cannot discern between 10-90 or 90-10 in this example. So again, if we are infrequent with our sampling, we're too late, we forget or we miss the opportunity to take that samples, we cannot quantify. Let's have a look at some water ingress now, moving away from oil. So we typically see water ingress at some point. Much of the time we don't actually know when the water is going to appear. We're never completely sure. So we've devised a way of qualifying to some degree the water cut, even in steady state conditions, and I'll explain this. When we're running water tracers, because we are in effect looking at the surface area and the exposed amount of that water tracer to the incoming water flow, it's important to look at that in reference to how much oil might be coming in, so in a multi-phase scenario. In this example, the nearest to the surface is 90% because it's a higher water cut because there is less oil covering that water tracer, therefore allowing more water to be exposed to the surface area of the tracer, therefore releasing more tracer in this example. Again, back to the surface area, this example I gave earlier, that has increased the concentration given compared with the toe end of this example, which is a higher proportion of oil, is therefore covering the water tracer more and then not allowing the water tracer to be dominant. Therefore the oil is dominant in this example. If I switch that around and show you a 50-50 example, you'll see both curves in this example are now the same. So we're getting a 50-50 water cut because we're finding that the tracer response is giving us this information back at surface when we do our laboratory analysis. And then finally, if we split that around the other way, you can see you can get the answer completely inverted, where the toe section of the well is providing more water cut than the heel section in this example. And that's important where you have a smart well, you have options for the future. You can shut that in, perhaps. You can stop that water flow. There may be something you can do. There may be nothing you can do in this particular well, but at least you know what water culprit is giving you the most problems and headaches. So the water tracer samples directly related to surface contact area and integration of response time over a comparative analysis so as the source water to be established. So again, water cut. This is not a quantified water inflow, but the water cut percentage of relativity. So let's have a look at some analysis and data. So yeah, the samples are picked up offshore, onshore, whatever the location happens to be. We ship these samples to a laboratory, whether that be on-site or off-site. We then look at how these tracers have been eluting, how they're being released from each of the zones. And we obviously have these individual characteristics because we know which tracers we put in the particular zone, therefore we know which tracers to look for. And this lab data analysis is important for future data history matching and obviously that knowledge of inflow profile for the future. And then we provide that report back to the client for future discussion. It's really important to look at the amount of sampling. I've said this several times now. Now let's have a look as to why that's the case. The following slides are absolutely the same data. There is no change to the data I'm about to present over the next 4 slides. What it's going to show you is the absolute paramount importance of sampling regularly. The first slide, 60-minute samples, 1 every hour. That's quite regular in some cases, but not in tracer work. If we move to the 30-minute slide, you can see there's more data being presented to us. It's a bit like a jigsaw puzzle. You miss parts of the pieces and you don't get the full picture. So 30 minutes is obviously half the time, but you're now increasing your data flow. Much more granularity is being given and more data. However, let's move to 15 minutes. You can see again the peaks, you can see the tails, you can see the shapes of the curves. And importantly, 1 every 5 minutes, which sometimes is required, you can see the tail section at the bottom right-hand sides of the curves are actually given even more data again. And it's important to look at that first upper slope, the transient phase as we hit the peak. Then you have the downward decline curve coming down the backside. And then as you move further to the right, that's when you hit steady state conditions where the curves are no longer curves, they're basically lines that are telling you that you've got qualitative response of tracer. So that's why it's very important to catch that first shape of the curve and on the backside of that curve as well. We'll talk a little bit more about that in the case studies. And here's just a close-up of that 15 and 5 minute. You can see, perhaps to the untrained eye, they look very, very similar, but there is greater granularity in data response given if you take 1 every 5 minute samples. So it's essential to collect frequently, especially after startup. We can actually set up offshore or on site, wherever they happens to be, at the client's facility to take samples and analysis at the site with our portable laboratory, delivering oil response, tracer response in an hour. So we have these multiple labs. Some of them are winterized for specifically cold conditions, or the North Sea. We have special labs available for the use actually at site. These are fully fitted out with our gas chromatography mass spectrometers. They have a very, very low rate of detection, down in the parts per trillion, and they can handle both oil and water. Now, the analysis that we provide is fed back through our proprietary software, FlowTrack. It takes all the initial data and then packages it back from an ideal theoretical response initially when we put the proposals out, and then when we actually look at the actual data that we received, we then compare and contrast that, and then we can actually put that detail, which zone is being flowing well, which one isn't, and in certain cases we can quantify as well. So let's move into the case studies. So I'm going to discuss 3 different case studies, and we'll start off looking at quantifying the inflow. So this one here, what we're trying to achieve here, this one is a Packard example, sliding sleeves. So each zone is known and it is segregated from the other. That's very important. So we know the location, we know the volume and the time difference between each one. So we have to assume certain conditions such as zero associated gas. We have the ability to take an oil swell factor into consideration. We need to have enough volume between each zone. Clearly, if the tracers are very, very close together, we don't necessarily always have the time to sample within that 5 minute regime because of the wells flowing very quickly. We could end up with the tracers coming at us too quickly to sample. And we obviously need to know the flow rate to surface and the volumetrics at surface, which we would do anyway. Then we look at the FlowTrack software. So we expect the time of return and shape of the curves in theory, and then we look at the actual. So this particular case study here, a 4.5 inch sliding sleeve, as I mentioned, a sliding sleeve arrangement, 17 degree API oil, with about 1,000 barrels a day. Now this red tracer is used as the baseline, the yellow clearly at the toe end of the well, and these ones have the pop joint, which was completion A from the previous examples of tracer install potentials that we can offer, and this was designed to last up to a year. So the predicted ideal tracer response, now this isn't going to happen in reality, but it's important for us to understand the timing. So clearly the red's going to arrive at surface first. Yellow would come last simply because it's at the end. Now you'll see the distances between the peaks. These are the time differentials. Assuming all things are equal for the inflow, these are the differences in time that these tracers should appear as they come back to surface. Now reality is something usually quite different to that. What you can actually see here is still the same peaks, bar the yellow, but you can see that the time difference now of red to blue is much, much closer than what you would expect. Then you've got the green and the pink coming out a little bit later, followed by the aqua coming much later on there. So initially what you noted there, no yellow, so tow zone wasn't flowing at all. This may be important for future drilling in that last X amount of 100 feet was not required to be drilled because we got such a poor response from the toe zone. Why should we drill deeper on the following well? That could be one example of using this data. And here's another good point, is that although you didn't get the tracer responses when you expected it, the point here is that you did actually get response from one up from the toe, eventually some hours later than was expected. So the cleanup took a little bit longer in this example, but the point is it cleaned up eventually. So in summary, we have a strong heel, an average performing midsection, and a relatively weak toe. So that would be a good picture to present for future drilling to say, well, was it worth going that deep? What can we do different next time? To get the quantification, there's a lot of information on this slide, but I just want to bring out the main salient points. It's important to understand that the time to surface. So if you remember, the blue and the red and the blue tracer in the initial predicted timing was quite far apart. What you actually see here is that the time difference is reduced considerably. Now, the only way that can happen is if you've got a stronger inflow pushing that tracer along, which is then speeding up the ability for that tracer to reach the surface. And that's exactly what happened here, is that the blue tracer is seen, as you can see there, 19 minutes. It's considerably shorter than what was expected. You know the volume, 8.8 barrels between each section, because that's the way the packers were laid out in this example. And the flow position between each can then, of course, be divided over to get the rate. And then we can start looking at taking the total flow and then putting a relative percentage of impact over those tracer responses against the total flow received at surface. In this example, the blue is the strongest section, and you can clearly see that there at over 50% flow. And this is the kind of picture where we start to put this quantitative data package together to give real numbers, something real solid to work with, rather than just, yes, you're getting tracer, or no, you aren't getting tracer. So using these timing intervals that we've measured, along with the rates and the volumes, we can use this in a transient time analysis, again, the transient build-up time of the well. We can use this concentration of the tracer for each zone to measure the inflow and give us this quantitative data. Now, there is another way that we can look at this in what we call the decline curve analysis. This is the backside of the curve. So remember, we talked about the peak, and then we talk about the downside of the curve. The backside of the curve, before you hit the steady state conditions, which are much further along that curve. If you look at the blue line here, it's rapidly declining. Again, because it's a higher flow, you cannot get the amount of tracer into that passing flow as you would if it was a much slower regime of flow passing by. Because that one is the highest flow, we rate that as 1, and then we do comparative slope analysis with reference to the blue, so that we then have a picture being built up of the shape of that decline. So again, the aqua being the poorest performer has got the highest concentration of tracer here. But the blue falls down quicker because it's been released into a much, much faster flow. Yellow clearly is 0. So this is where we normalize, steeper curve. Then we look at the figures again. Now, again, a lot of information on this slide, but the main point is that based on this comparative flow that we're working out from the slope, compared back to 1, the blue, we can see that our numbers are very, very similar to the transient time analysis. So we're about 1% of a differential between the two methods. So it gives us the confidence in conditions where we're running packers, ICDs, sliding sleeves, where we have that confidence that we know our volumes absolute. We have the ability to then give real good quality firm numbers to this particular well installation. Case study 2, I'm going to talk a little bit about the water side of it. This is, of course, as you may recognize, a wire wrap system. We are involved in the installation phase prior to these end caps being welded on during the manufacturing phase. Clearly, we had no other way of getting the tracer in. So that means it's ensconced within the wire wrap system so that when it's shipped offshore, it's exactly in the location where it's designed to be installed at. This is a 6 5/8, 3 screens per tracer type. and it was actually a two-branch multilateral. So clearly in a single mother bore where you have got a multilat, it is very difficult to know which zone is the culprit for the water inflow. So this is where tracers come into their own. So we can see here, simply by looking at the surface area exposed and the actual concentration received back to surface, we're managing to understand that the lateral that contained the T917 tracer was giving out the biggest amount of water inflow. And again, if we have the ability to allow the customer to make that conscious decision to make a change, if it's possible, the cost savings is absolutely imperative to the future of the well, future of our business, and full stop. If we can save money on handling water back at surface, then all the better. So the final case study that we'll talk about in a little bit more detail, I certainly recommend you download this paper. It's a very good paper here on the Shell Argonauta O North 26054 OTC paper that was presented this year. We can hopefully get a copy of that paper during the archive version of this to you, if possible. What this actually does is cleverly uses, off the east coast there of Brazil, not just inflow tracers, but also interwell tracers, which we also provide for injector-producer relationships, where we can look at the data provided from the injection of the waterfront from the injector through to the producer. So this one uses a hybrid system of both inflow and interwell. It's a heavy oil field, 16 API. It's not particularly warm, 57 degrees Celsius, so no issues for temperature concerns there. We typically would say up to about 175 degrees Celsius for our polymer tracers, and up to 10,000 barrels a day of production. So we just break that down and to show you how we placed all these tracers, as there's a significant amount of tracers used in this well. So we have 4 injection wells, as you can see on the map there. 7 producer wells. 1 unique water flood interwell tracer was injected into each of these injection wells. So that's a total of 4 water flood tracers. We have 4 inflow water tracers in each of the 7 production wells, which is, of course, is 28 inflow water tracers. And then we had 3 inflow per 7 of the course of 7 wells at 21 total inflow oil tracers. So clearly a large amount of tracers being used here, and the identifiability of them has to be paramount. Is absolutely crucial to be seen that they cannot be confused within the presence of each other, which is why this project was designed this way, with very, very unique, distinct tracer pattern. What did we want to try and achieve? Okay, well, interwell connectivity, reservoir sweep efficiency, something else that we can help to achieve with our interwell tracers. Improved interpretation of the high permeability channeling between the injectors and producers. The points of water influx in the production wellbores. Where is this water coming from? Oil inflow profile along the production zones without any intervention or PLT. Give indications of how well the well cleaned up in the long term and in long horizontal wells as well. The placement here was chosen across the wire wrap screens. So these were in the sand screen between the base pipe and the filter, within that drainage layer that we talked about, so you can clearly see there. And these encapsulated these strips prior to the end caps being welded on. And then we had a liquid polymer injection phase across the sand screen, the mesh, where we put the polymers in across the screen. And here we see the tubes that contain the tracer and the hardening material being injected along the pipe. 32 unique water and 24 unique oil tracers manufactured in total. So, based on the geological sampling of them and the logs acquired from the drilling phase, we were able to place the tracers in a particular pattern of unique types of tracer to allow us to get the best possible chance of getting the good data back that we needed to have. We had a situation where we used water oil, as you can see down the bottom there, positioned perfectly for the data capture. Now the sampling, back to that sampling again, how important it was. You can see the schedule here for the first 24 hours. Actually 10 of that first 24 hours was done at 1 every 5 minutes. It's a pretty intensive cycle, but it's important to, of course, do that as we previously discussed in the earlier slides. We then can relax that a little bit from the 10th hour point through to the 17. We're looking at 1 every 10 minutes, and then for the remainder of that day, we are down to 1 every 15 minutes. The 5 minutes, crucial again to understand the build-up of that transient phase of the well to capture the important data as it's coming at us from the very, very outset. For the long-term aspect of the well, we can really relax the schedule because we're looking at more of a qualitative example here. So we don't need that rapid, quick sampling regime. And you can see here as we move up to the 56-day mark, we're taking samples up to once every 2 weeks. So starting off, once every half day, once every day, through to 7 days, and then on to 2 weeks. So therefore, you're looking at qualitative information at this point forward. Still giving you the data that the tracers are releasing. Therefore, you're still getting an inflow of either oil and or water. This information was put into our proprietary software package, whereby we analyzed the results. And here we can see the results. Now, I've just chosen one producer here for the interest of time. There were several to look at, but here is just one example where we're looking at the well startup time, corrected for the subsea flowing volume, and the well shutdown time for each of the 4 tests. This is important that we know when the well started and stopped, of course, so that we can then understand the volumetrics and the timing that's coming back and the information that we're giving. So looking at test 1 and 2, you can see here that we're getting a response from all the tracers, and we're getting a higher response of tracer towards the toe end of the section in this particular example. And then we can start putting that relative quantification into practice, starting to do our numbers, working our numbers, and give the customer a real tangible degree of understanding of what that well is behaving. And here we just apply it in a pie chart format. We can see that the tracer response is considerably higher at the toe end. For test 3 and 4, we get pretty much the same results. We're continually seeing strong, good toe flow data here from the well. We're getting response, of course, from the other sections, as you can see there in your percentages. But again, we're getting good continuous flow coming from the blue section. And in the pie chart, this gives us this distinction here. As a summary, this section is showing us that the heel was providing about 1/3 of the total oil flow, with the mid about 16%, and the toe is actually 54% was actually being delivered here in this example. We also looked at the water. The water analysis is of course important to determine the source of the culprit, of where that water is coming from, using these individual tracers in a commingled production riser to allow that detail of information to be split from each of those zones. Seawater injection well broken through, and that's to date, and then 5 producing wells produce information water from the interwell test. And the mass of the inflow tracer calculated, integrating the concentration of each tracer over time with the water flow through the sample location. And it's important that we do that mass balance of looking at the tracer coming back from what we put in. And the trace responses are corrected for the surface area variation. So we have to understand the well, and the detail is extremely important that we do that so that we can then give quality data back to the customer. So at this point, I'd like to ask you a second poll question. Now that you've heard some details about the tracer and the background of it and the benefits I'm hoping that you're realizing is out there for your potential future wells, would you care to please answer a question on this multiple choice? Which one do you feel is more beneficial to you in your response? Would it be critical to your business, using the reservoir management, using tracers? Maybe a little bit beneficial, or not at all. I'll give you another 20-30 seconds to answer that, and then we'll have a look at the results. Okay, I'm going to now push these results to you, and you're going to see that that's an interesting split. That's good. 80% of the audience think that in a number of cases would be beneficial, and even 16% absolutely critical. So it's good to know. Thank you very much for answering that question. And I'd just like to finish off with a couple of the last of the slides. We talked about this produced water data analysis, and the good thing about using this is not just graphs. We can present it in bar charts. So when you're looking at a number of zones, a number of wells, it's going to get very confusing looking at a number of graphs. So we do the crunching work, we do the hard work, we provide these bar charts so that when you look at the well contribution, you can start to see which ones are the biggest culprits of this produced water. And we are matching this up against the multi-phase flow meter measurements. So these are the 5 wells that are showing the production of water and the percentage contribution from each. Clearly, looking at the second row, you can see which of those wells overall were the largest contributors. So ON10 in this example was clearly the largest producer overall. And that again could give the customer an opportunity to make a future decision based on that valid, very important data that could really start to help develop that field for future completions that are being planned. So what did we manage to achieve? Just to summarize, these were open hole gravel packs, so we have to assume that because they're gravel packs, we're not getting any annular flow. We've confirmed that the clean-out has been achieved in these production wells. We have given the client quantitative data on the oil inflow for each of these 7 wells with independent tracer usage. And this can be now used along the geological data alongside to refine future reservoir simulation models, history match, put it into the new model, and then be able to make informed choices, decisions for predicting future flow. Determined that the 5 wells have started to produce water after detection at the surface within the common flow line. We have confirmed that the positions along each producer has been flowing into each well, the water. And we also confirmed that 1 seawater injection over the period of time has actually broken through. And we can now optimize that water injection schedule to best suit that particular reservoir. So in summary, sampling and tracer analysis, continuing allowing confirmation of further produced water source as this project's still live. The injection water breakthrough can then obviously be analysed for the interwell section as well as that data comes in a few months' time. And analysis of the water flood tracer curves then allows channeling and the sweep efficiency to be established once the additional data is generated. And now I'd like to close on some questions. We have a few questions here coming through.
Stuart, just want to say that the audience, you can continue to submit your questions by using the Ask a Question box located on the lower left corner of your screen. So, Stuart, go ahead and start with the first question.
Okay, let me see. So we have a question here from Edha Ramirez Slumberger. How can you differentiate from flow inside the wellbore and behind the casing? Just a second here, sorry. Yeah, sorry, that question has not come up here for some reason. Apologies for that.
Do you want to come back to that question, Stuart?
Yeah, I think what we'll do is possibly come back to that question. I'm not getting all the questions coming up here on my screen. Apologies for this.
If you like, I can ask the other questions.
Yeah, let's move on to. I'll come back to that one.
The next question is what's the effect of these tracers in HGOR wells?
Okay, yep, from Baker Hughes. Guillermo, thank you for that question. Yeah, these particular wells that we're talking about here are either oil or water inflow. The tracers are designed to work in a wet flow environment because of the mechanism. Now, we can use gas tracers in interwell and we can use them in frac tracing. However, when you have very high gas, it's the main product, then we cannot use inflow tracers for that because of the dry flow. However, if there is an element of any oil, then that would still be usable. We could still look at potentially using the inflow tracers. And of course, if there's any wet water flow, then we can use water tracers in this example. But if it's a gas well, then we're unable to use inflow tracers. Okay, let's move on to the next one. The possibility, so Lime Rock Partners, Sally, thank you for that question. What is the possibility, feasibility you have gas tracer technology? Well, as I mentioned, we do have gas tracers that we can use in interwell, of course, and frac tracing, but they are working on a different mechanism. Current technology won't allow the ability to run this because simply we need this wet flow over the tracer to initiate the molecules of tracer that's embedded within the polymer for it to be released and have that flowing out with and into the passing flow stream. So unfortunately, at this current states, we won't be able to provide a gas tracer technology for inflow. Okay, next question. Is there an effect of these tracers when used with artificial lift systems, rod lift, gas lift, DSP, PCP, jet pump? The simple answer would be no, but we need to know about them, simply because they would affect the flow regime. The point here is that these tracers are literally passengers with the passing target fluid, so the fluid being pumped along the oil, once it's tagged, the oil isn't going anywhere. There is a high affinity, high propensity for the tracer to be attracted to the hydrocarbon, and once it's locked in, it's not going to leave. It's with the oil or with the water. And because of this partitioning in from the oil, effectively as it's passing, we are sure that what the answers we're getting back means that the tracer is there. It's not going anywhere other than within that oil phase movement. So the effects of these, they would have an effect to the point of obviously changing the flow regime. And obviously the timing element could be changed there. But if we know what the pumps are doing and what the system is producing, then we could make some caveats to that calculation. And we would try to manage that best we could to understand what's been happening. But it doesn't stop you using the tracers. That's the main point here. You can certainly use them. And even if the quantification is not possible, then you've still got that qualitative answer there, yes or no. Okay, next question here. From Shell. How the tracer evaluation shown in your presentation can be applied to oil, water, chemical tracers injected during fracture stimulation or production contribution accuracy in unconventional plays. Oh, sorry, my screen's just refreshed now. Okay, let me have a think about that. Well, we are running fracture work right now with our tracers. We are able to inject tracers through, let's say, into the fracture stimulation stage of a proppant. So we're running oil, gas in these conditions. So we can run gas tracers, as I mentioned before. We could employ the use of these tracers if you were perhaps using a fracture simulation that was requiring tracing. We could also, if we were using sliding sleeves, use the inflow. So there is an option either way there. One good thing about the fracture tracer choice is the ability to quantify, because once the oil transitions, the gas transitions into the hydrocarbon. We have a known quantity that we put in, and therefore we have a mass balance known what we get back out. So we could actually use any hybrid. We could use up to all three different types if the well required it. Because these tracers are unique, we could actually use this to give a good example of what the well's trying to tell you. So hopefully that answers the question. Okay, next one from Marathon. On the first sleeve example, internally vented tracers, how do you account for contact with water pre-stimulation, which can be several weeks before doing a frac job? Does it not dilute the results? Well, let me think about that. I'm assuming this means that if the well is staying static and you have tracers in situ in the inflow, if the water's contacting, yes, you're going to get some release of tracer. We are seeing wells that are being put on hold for a number of months before they're being flowed. So we have to take that into consideration when we plan our operations. But we can protect the tracer to a degree to protect it from releasing too much tracer too quickly. These are very, very sensitive. And if they come into contact with the targeted fluid, they will indeed release tracer immediately. And the last thing we want to do is have a situation where the tracer is being released very, very quickly over a period of time where the well is shut in. So ideally, that's what we want to do, is protect the tracer from flowing too early. It's different in frac tracing where the stimulation fluid, the fluid is being pumped in. Water is sitting with the pad that's being injected. So it's a different mechanism completely as to pumping liquid tracers as it is with solid tracers. Question on, can we have a copy of this presentation? Yes, it's going to be archived, and we're going to have a link to get that downloaded so you can use it for future discussions. Next question from Oxy. Do you see a correlation when comparing the tracer data to a PLT? Well, it's a very good question. We are looking to work with a future client where we see a PLT and a tracer being run in the same well. And as that beauty of a correlation is ideal to show the benefits of what the tracer is providing. Typically, you run one or the other, which is unfortunate when you're trying to prove what tracers are doing against a PLT. You never or normally have the opportunity to have the same well. However, we're going to look at that and we're going to get that data. And I think what we're going to see is some really interesting results from that. So we have good faith that we will get good results when we compare that data to a PLT. And we look forward to getting that opportunity in the future. Next question, Holly Consulting. How are the tracers retained in the polymer over the life of the well? Well, the polymer is a solid object and it's not moving, it's not going anywhere. The tracers are in the spaces, in the minute spaces in between the polymer, the chemicals are located. So there is only a finite amount of tracer available, which means there's only a finite amount of lifetime available to the course of the well. But the point is that even though the well has used up all its tracer, shall we say, therefore we simply stop sampling and the project is over in terms of tracer life. It doesn't affect the remaining life of the well when the polymer is still there in situ, because as I talked previously about the blockage or the space that we take up is engineered to be minimal as possible so that we do not upset the inflow of this targeted fluid over the period of time that this life of well cycle occurs over. So again, although the polymer is there, it won't affect the future of the well performance, but the tracer will have a lifetime, and that may be designed to be X amount of months, or it might be a couple of years, 2-3 years, depending on the well scenario.
Stuart, we have time for one last question.
Okay then, let me just see, there is a lot of questions here that's coming up on my screen now, so let me just pick one here.
What will happen is we have a very interested audience, and what we'll do is we'll get Stuart to answer these questions offline in the next day or two.
Yeah, that might be a good idea. Okay, thank you, Pramod. Okay, there's a couple of questions here on the same topic, so I'm gonna pick this one. Effectively, the great question from Lime Rock here. Can this be applicable to cemented liners or casing? So, yeah, I would love to be able to provide that service right now and say that we can do this. Now, we have got perforation tracers so that you can qualify which zones are being produced once the guns go off. But this is not really what we want to try and achieve. We're trying to get to quantification. Now, to achieve that, it's very difficult, as you understand, to get the tracers in position to run with a cemented liner or a casing, simply because of the nature of the construction of that well. There is a possible way of doing it where you hang off a tool inside. Now, that's probably not going to be a very attractive idea to the clients, but it is possible to hang off a hanger tool with a pup joint full of tracer material that is in direct inflow for picking up the targeted fluid with the tracer in it on the way up to surface. Yes, it's adding something to the well that's not been designed to take, but it does give you the option of at least qualifying which zone is producing, whether it be a tool section that you're trying to confirm you're getting good cleanup from. It's something that could be considered, but in terms of polymer application to the liners or casings that are cemented, not at this time. Perhaps in the future we'll be there, but it is a good question, and it is one that we see being of great value for the future for our clients. Okay, I'm sorry we've run out of time here. I'm amazed at the amount of questions, so I really appreciate all the questions coming in. Sorry about that first one. I had a problem with my refreshing of my screen. So again, I apologize about that. But as Pramod said, we will answer your questions over the course of the next few days to at least give some insight as to hopefully give you that insight to the answer that you're looking for and help you make any decisions for the future for your wells. So at this point,
Stuart.
Thank you.
We'd like to thank everyone for attending today's webcast. We especially thank Stuart and Tracerco for putting together this timely and informative presentation. Finally, an on-demand version of this conversation will be made available within the next 24 to 48 hours, and it will be emailed to everyone. Thank you and have a great day. Good morning or good afternoon, depending on where you are in the world. And welcome to today's webcast, Cost-Effective Long-Term Fluid Inflow Measurement Without Wires or Well Intervention. I'm Pramod Kulkarni, Editor-in-Chief of World Oil Magazine, and I'll be your moderator today. During today's presentation, you'll learn